Hello everyone and welcome to Solved, where we help you solve problems. In this video, we will be talking about the temperature change of a fluid flowing through a nozzle. Nozzles are thermodynamic devices that decrease the pressure of a fluid in order to increase its velocity. And we are here to determine if there is a temperature change associated with the process. Here's the problem statement. Air expands adiabatically through a nozzle from a negligible initial velocity to a final velocity of 325 meters per second. Determine the temperature drop of the air. Before we proceed with the solution, one thing to note here is that the outlet velocity is actually very fast. 325 meters per second is very close to the speed of sound in air at 25 degrees Celsius, which is around 346 meters per second. That means that the outlet of the nozzle is nearing sonic flow, but for now it is still in the subsonic flow region. Let's go ahead and solve that problem. Here is our illustration of the problem. We have here the nozzle that expands the air adiabatically from a practically zero velocity to a very high velocity of 325 meters per second. We are required to determine the temperature drop of the air as it passes through this nozzle. Since this is a steady state open system problem, we can go straight to our energy balance equation. The first law of thermodynamics in this case would be the mass flow rate of air multiplied by the change in enthalpy of the air plus the change in kinetic energy plus the change in potential energy is equal to the rate of heat transfer plus the rate of work transfer. Since it was stated that the system is adiabatic, we can cancel Q, and for nozzles, there is no shaft work. For a horizontal nozzle, we can also assume that the change in potential energy is very small, such that we can assume the value to be equal to 0. What we're left with are the contributions of change in enthalpy and the change in kinetic energy. Our equation now simplifies to 1/2 U2 squared is equal to negative delta H. We have simply transposed delta H to the other side of the equation and we canceled U1 squared. Since we are after the change in temperature of the air, we can expect the temperature to play a role in the change in enthalpy of the gas. We write the delta H, or the change in enthalpy of a gas, as the integral of the heat capacity times dt from the temperatures T1 to T2. We can simplify this analysis to simply involve the average heat capacity of a gas, that would be Cp average, multiplied by delta T, that is T2 minus T1. Remember that we are after the value of delta T. Our equation then becomes 1/2 of U2 squared is equal to negative Cp average times delta T. From this expression, we can isolate delta T. We have delta T is equal to negative 1/2 times U2 squared over Cp average. At this point, since we know that our substance is air, we can simply look for the heat capacity values of air. However, we are not sure of the temperature since there were no given inlet nor outlet temperatures. For that, we have to assume that air is an ideal gas. For ideal gases, we have a value of Cp. For diatomic gases, that is 7/2 R. We can use this simplifying relationship to determine the value of the average heat capacity of air. This assumption is also valid because air is mostly composed of nitrogen and oxygen, and both of those are diatomic substances. We do have to convert the units of this because R is 8.314 joules per mole per Kelvin. We want to be substituting joules per kilogram per Kelvin. So for that, we have to divide this with the molecular weight of air in kilograms per mole. So that is 0.029 kilograms per mole. With that, we are ready to substitute and solve for delta T. Delta T is negative 1/2 outlet velocity squared, 325 squared, divided by 7/2 R, that would be 7/2 times 8.314, divided by the molecular weight of air, 0.029 kilograms per mole. Our change in temperature is negative 52.63 Kelvin. This means that as our gas passes through the nozzle, its temperature will drop by 52.63 Kelvin. We do have to keep in mind that we made several assumptions for us to come up with this value of delta T. For example, our delta H, or our change in enthalpy, was only based on the sensible heat change of air. Therefore, this approximation will not work for very, very low temperatures such that it has the capacity to condense air. Also, since we have assumed that air behaves ideally, we really cannot use this approximation for very low temperatures. But for ambient conditions, this approximation is suitable. That's it for this video. Thank you for listening, and this has been another problem solved.